Good morning, everyone. We would have done a lot of this stuff in class. I'd prefer to do that, where you guys can talk to each other, we can talk as a group. But, sometimes your body just turns itself inside out and vomits your entire guts out into the sink overnight. So, missed class, so we got to make up for it this way. There's going to be certain points during this video where I'm going to ask you to stop, to pause the video and think about something, jot something down. Oh, I just jammed my knee into the counter. Ow. So please do stop it at those points and give yourself time to think and write things down, make a few notes, because if it's just me lecturing at you, it's just known that you're not going to learn it. You might sit there and be like, yeah, okay, yeah, I got it. That made sense. It's not really going to make sense. So please trust me on that. Stop it when I ask you to stop it. All right. So you guys have been working with the idea of energy and temperature, heat and temperature. So remember, we can use heat and energy interchangeably. Those words mean the same thing. But temperature is a related topic. You guys have your 2-degree challenge reports back with lots of comments. Please read my comments. They're mostly questions, kind of a back and forth with you, because I really do like finding out how you guys are thinking. You often bring up things that I find very fascinating that I want to follow up on. So if you haven't already, take a look at the comments on your 2-degree challenge lab report. And what you guys were working with there was, if I want to make a temperature change happen, a lot of you guys were like, okay, so if I want to make a temperature change happen, I have to add energy, and because there's some relationship between those two things. So I'm going to give you an example. Let's say you have oh God, how do I draw a bike? It's like that and that. Oh my God, something like that. And like, meh. All right, and then it has a seat, otherwise it'll be uncomfortable. So there's a bike. Here's a car. This is really very well done. And then here is a truck. Okay. So you got these three things, right? Bike, car, truck. You're going to come up. So here's you. You're looking really good. Looks just like you. You're wearing a top hat. And you're going to apply the same amount of energy to each of these things, all right? So you're going to walk up to the bike and you're going to push on it. So you're going to provide some energy to it. You're going to walk up to the car and you're going to push on it. You're going to provide some energy to it. And then you're going to walk up to the truck and you're going to put some energy into it. So we're saying Q is a certain amount of energy. A certain amount of energy. Okay, so now what I want you to do is I want you to pause the video for just a moment and just write down your predictions for what's going to happen. All right, so in turn, it's not all happening at the same time. You could say we're doing this on different days. One day you walk up to a bike and you push it with a certain amount of energy, a certain amount of force. The next day you go up to a car. You push on it with a certain amount of energy. Same amount of energy you applied to the bike. And then the third day you apply the same amount of energy. You push just as hard as the other 2 times, but this time you're pushing a truck. All right, so now you're going to do, what is your prediction for what will happen? So pause the video, think about that. All right, so now you're back. You got your prediction, right? You figured out what you suspect will happen when you add the same amount of energy to these 3 different things, right? So when we look at these things, there's differences between them, all right? So we've got the bike mass. So we know some of these things are lighter and some are heavier. So the bike mass is less than the car mass, which is less than the truck mass. So we know from personal experience that it's harder to push things that are heavy, that have a lot of mass, than things that are light. So all other things being equal, if you apply the same amount of energy to each of these things, it's going to be easier to get the thing that's lightest, the thing with the least mass, moving. So for the bike, it'll go far and it'll go fast if you push on it pretty hard. But if you apply that same amount of energy to the car, I don't know. I mean, I have some things I'd want to ask about pushing on this car. Probably should ask them about the bike too. But I think I might be able to move the car. Might move. And then if I apply the same amount of energy to the truck, probably won't move. Now, I don't know that for sure because there's other things that are going on here, or could be going on here. But just if I'm basing it on all else being equal, the light thing, the medium thing, and the very heavy thing, I'm probably going to get the light thing to move based on the energy I put into it. I might be able to get the car to move a bit, and then the truck I probably can't move. All right, so that's just based on mass. Bigger things are harder to move because they have more mass. They have more inertia. They're made out of more stuff, and every single molecule, every single atom in this truck, if we imagine that it's made up of like these gajillions of particles, if I want to get that truck moving, I have to move every single one of those molecules. Each one of those molecules needs to receive some energy and get moving. And so the odds that my little push is going to be able to get that much mass moving is just kind of low. So that'd be my prediction. I'm going to clear some of this stuff away. All right, so we're applying that same amount of energy. Oops, I shaved off the top of the truck. Okay, getting rid of this stuff. All right, so we know the mass thing is true. All right, so now I want you to think about what would be different, right, if, now instead of this scenario as we've been imagining it, take the top back on the car, let's imagine that this truck is sitting on a hill like that, and it's in neutral. Let's imagine that the car is sitting on a flat surface, and it has e-brake, emergency brake on, and then the bike is sitting at the bottom of a very steep hill, or sitting in the middle of a very steep hill. All right, now you're going to do the same thing. You're going to apply the same amount of energy to each one of these things. All right, so you come up to the bike, start trying to push it, it's sitting at the bottom of a hill. You try to push the car, it's sitting on a flat surface, it has its emergency brake on, it's in park. And then the truck, you're going to apply your energy to, and it's sitting at the top of a hill, and it's in neutral. All right, so same amount of energy applied to each of these three things. Stop the video again, take some time, write out a little paragraph, make your prediction about what will happen now. We had a prediction before we knew anything about where these things were located or any of these specifics. Now you're going to say, has anything changed about your prediction, and if so, why? So pause the video, work on that. I'll see you in a minute. Okay, so you're back, made some predictions. All right, so you probably have a general sense from being alive in the world that this changes a lot. Right? So things can be easy to push or difficult to push, not just based on how much stuff they're made out of, not just based on their mass, but their situation. Basically, what other forces are working on them? And are those forces working with you, or are they working against you? All right, so when I look at this, so now that I know this bike is sitting at the bottom of a steep hill, I no longer think it's going to be quite as easy to move as it was before. It's still very light, but now I'm pushing it up a steep hill, and that's going to be a pain in the butt. So now my Q is not going to make as big a difference. Now, if I go to push this car, all right, it's on a flat surface. So that's kind of like, it's not working against me, but it's not working with me. But this car has its emergency brake on. I mean, you can push a car, but generally you want it to be in neutral. Because if you're pushing against a car that has all of its brakes engaged, the force that you're working against, so there's something fighting you. Right? And so your small amount of human energy isn't going to be able to move that car if it's got all of its brakes engaged. Once a vehicle is in neutral, though, you don't have as much working against you. You're not fighting against that force that way. So that's the example of the truck. So the truck is in neutral, so you don't have brakes that you're working against, and this truck is at the edge of a steep hill. So your amount of Q, when you go to push on this with that same amount of energy as you push the car with, now you're probably going to get that truck going, and it's going to roll down the hill, and you're going to lose control of it. So now our prediction has changed a lot. So we still care about the mass. The mass is still involved. But we also have to consider what forces are either holding that object in place currently, or what forces are tending to make it move. So if we look at gravity, gravity is pulling this truck down all the time. If you give it a little nudge, then gravity is going to do the rest. So there's not a lot of force holding it in place. It's only going to take a little push to get it moving. This car that has the brake on, there's a lot of force holding it in place. There's a lot that you're fighting against. So you're probably not going to be able to get it moving. Here with the bike, it's quite light, but you are working against gravity. You're working against a force that's opposing you. So your amount of energy that you're putting into these three things is going to have a different effect depending on what you're pushing. So what I want you to consider is when you're doing this in chemistry, we can't see the things that we're working with, So we can't necessarily have that immediate sense of like, oh, that's a light thing, that's a heavy thing, that's a medium thing. But we want to consider the mass when it comes to trying to determine what's going to be the result of putting energy in. But we also want to consider what forces are working against us. So you can kind of think of it as, so energy is the cause. So you can either put energy into something or you can take energy away. And temperature change is a possible effect. Now, what do I mean by that? All right, so in this case, we're applying the same energy to each of these three objects. So this Q, this Q, this Q, these energies are all the same. But the effect on the truck, the car, and the bike is different. They respond differently to that energy. So energy is the cause that you're applying. It's kind of the force that you're applying. And then what we're going to observe is, did it have an effect? So in some cases, if you're pushing on a car that has its emergency brake on, you're putting a lot of energy into it, but it's not really having any effect. It's not moving the car's not doing anything. Same thing is going to happen with particles and molecules. Sometimes you may put energy into them, and they just won't show any effect. And so we're going to look at temperature change as that possible effect. So I'm going to show you guys, we did that example of where I told you you're going to take a piece of metal, right? And you're going to heat this metal up to like 700 degrees Celsius. I don't even have a sense. That's like really, really hot. I have no idea. But then what we're going to imagine, and you guys left off with this before I got super sick, you're going to drop that metal into the ocean, specifically. We're going to put it in the Atlantic Ocean. So this is sizzling hot, beyond sizzling hot. And the Atlantic Ocean is, maybe like, I don't know, let's say it's 15 degrees. I can't even make sense of that. Yeah, I guess it could be in a certain place in the world. 15 degrees Celsius, you're going to drop this super sizzling hot piece of metal. Because the question was, when you add energy to a substance, does it always result in a temperature change? And we didn't have a lot of time to talk about this as a group. But as I was listening in, as you guys were talking to each other about it, most of you concluded that when you look at the entire Atlantic Ocean, even if you drop this super hot, this like radiating, sizzling hot piece of metal into the Atlantic Ocean, you're not going to get any change in the overall temperature of the Atlantic Ocean. Overall temp of the ocean after plunking this into it. Now, some of you guys pointed out that doesn't mean there will be no effect. So if we look at this metal cylinder, we kind of zoom it in and look in close, what we might probably see, some of you guys pointed out, if you drop metal that hot into the water, you're going to see steam rise from the ocean. So what you know when you see steam is that some of these water molecules that were sitting around minding their own business when this metal cylinder arrived from seemingly outer space, some of them got going so fast that they were actually able to launch out of the ocean. So they went flying up as steam. And even the ones that didn't turn into steam, if they were in the neighborhood when this thing arrived with all of its energy, with like all of its energy radiating out, some of these guys got going pretty fast. So they went zooming off as the particles that are in this metal were vibrating around and slamming into them, knocking into them, and they get going really fast. So the immediate effect, the very local effect of adding that metal definitely changed the behavior of some of those water molecules. But what we were asking is, did it change the temperature of the ocean? So this gets to a question of how do we define our system? So system means something different in chemistry than it does in a lot of other contexts. System means, we define from the beginning, all right, I'm going to take this piece of metal and I'm going to put it in the ocean. And what I'm interested in is, how did the ocean change its behavior? How did we change what we observe about it? So in that case, we're defining the entire Atlantic Ocean as our system. And we're looking at, did the temperature change in the entire Atlantic Ocean? Now, if we had defined our system differently, if we had said, just in this area, right? So you can do that. You can say, no. What I'm interested in is, was there a temperature change in the 1 liter of water around where that metal cylinder was dropped? Now, if that were the case, we probably would see a temperature change in that system. So what you always have to ask yourself is, okay, what am I looking at? Like, am I trying to define the change in this really giant system like the Atlantic Ocean? In that case, no, this little piece of metal doesn't make a difference to the entire Atlantic Ocean, but it does make a local difference. So if we're focusing in on the water right around the cylinder, yes, there's a temperature change. If we're looking at the entire Atlantic Ocean, no, there's no temperature change. So the question there is, how can that be true? How can you have both answers be right? How can it be, yes, it makes a temperature change, and no, it doesn't, just based on this quote unquote system that we're defining? So this comes back to, we did, the last video I posted was this Boltzmann distribution thing. So this is number of molecules over here. And then this is energy, right? So what we did last time is we went in and we were like imagining they were taking a sample of molecules. So in this case, we're going to imagine that we're taking a sample of water molecules from the ocean, right? And we know that the temperature of the ocean, we've defined it as 15 degrees. So 15 degrees Celsius. And then what we're saying there, what we mean by temperature is the average kinetic energy of this system. All right, so then when we go into the ocean and we say, all right, now I'm going to go and I'm going to like start picking out water molecules. I'm going to imagine that I can kind of get a stopwatch and watch the water molecules go by and time them. And so what we find when we do that is some water molecules are slow. They're low energy. Some water molecules are high. And then a lot of water molecules are somewhere in the middle, right? So we start, kind of timing these things. And we'll start to see that curve emerge. So I just want you to see how these are constructed again. So there goes a fast one. There's a really slow one. There's medium speed, little faster, slower, faster. And so when we do this, we start to add these guys up. We start to kind of pile them based on how fast they're going. So we get a lot that are kind of medium speed. You get some outliers. You get some speedy guys. You get some really slow guys. But most of the time, if you sit there long enough and you start to kind of stack them all up, this is kind of mesmerizing. I'm like amusing myself here. You'll get something that looks kind of like this. You're not trying to make a curve of this shape, but this is just what you get. All right, so we get what we call a Boltzmann distribution. So you have some speedy molecules out here, the really extremely fast ones, and you get the really slow ones down here, but most of them are somewhere in the middle. So we end up getting this kind of curve that's sort of shaped like this, like a bell curve. And what we're looking at, I got this a little off center, we're looking at the average, right? So the average molecule is going about this fast. It has about this much energy. And that doesn't mean that they all have that amount of energy. It's a range. Some of them are going slow, some of them are going really fast, but a lot of them are kind of in the middle. They're like the typical ones are in the middle. So that's what we're looking at with our ocean, right? We have some really slow water molecules in the ocean, some really fast ones, but the bulk of them are kind of, it piled up in the middle like that. Now, when we add that flaming hot piece of metal, what we see is that, a few of these, so like a couple of these get moving faster. No, my God. A few of these molecules get going faster. So they're like, and then this one goes, so and then maybe this one get going a little bit faster. So we see a few molecules, the ones that are right around the cylinder when it gets dropped in, we see them make a big jump in their behavior. They start moving a lot faster. But the key is there's only a few of them. Because when we look at the entire ocean, if we're really piling up, how many molecules are in the entire ocean, oh my God, we can't fit enough dots in here to represent them all. So the idea is, even if a few of these guys get going faster and they kind of jump on our graph, now we've got a dot here, we've got a dot here, we've got a dot here. The bulk of them, we still have these gajillions, quadrillions, quintillions, like unimaginably large numbers of water molecules are all still sitting over here because most of them are thousands of miles away from that cylinder and they have no interaction with it whatsoever. So the reason why we can have this confusing idea where we take this cylinder and we drop it into the ocean and we see steam and we see sizzling and bubbling and obviously there was an energy transfer and something happened, it's because it was so local that it was only a few, basically a handful of molecules that felt anything from that addition of energy, because that addition of energy was so small in the scheme of things that it didn't budge this distribution. Because what we're trying to do when we're looking at changing temperature is we need to shift this entire curve in order to get a temperature change, right? So if we're going to see if our temperature is saying what's the average kinetic energy of all these molecules in this system, if we want to see a temperature change, like this little change in T, we need to move a lot of these molecules into that higher energy level. So we need to get this guy going and this guy going and this guy going. They all need to start moving because we need to shift the average, not just get a few of them going, but we need to shift like a large number of these guys so that then our whole curve, our whole Boltzmann distribution is actually shifted over to the right to see a temperature change in the entire ocean. So you have to get a huge mass of these molecules to feel that energy. You'd have to provide way more energy than that little metal cylinder can provide in order to shift this curve so that our temperature, our average energy, is higher. So I know that's confusing, this interplay between energy and temperature, because you can add energy and not see a temperature change. And this is why, because temperature is not telling you anything about a specific molecule moving faster. Temperature is telling you the average of all the molecules in this sample, on average, they're moving faster now. The whole bulk of them is moving faster. We still have some slow ones, we still have some fast ones, but the bulk of them now are moving faster than they were before. And that is going to take a lot of energy for something like the whole Atlantic Ocean. So finally, I'm going to leave you guys with something that's new, and I'm going to have you think about this. I'm going to pull this up. All right, so this is a bunch of Boltzmann distributions. Now, we have been talking about temperature as if it's only about speed, right? So if you take some particles and you add energy and you get them to move faster, then you'll see a temperature increase. If you get enough of them moving faster, and on average they're going faster than they were, that's a temperature change. So we've been talking about temperature like it's synonymous with speed. But in fact, when you look up definitions of temperature, you'll see that temperature is the average kinetic energy of your sample, of the molecules. All right, so what I'm going to leave you with in your assignment for when you come into class on Monday after spring break is to have written up a little response to this, right? So you're looking at Boltzmann distributions here. So down here, we are looking at speed. This time we're literally looking at speed. So this is very slow molecules down here, and this is very fast molecules down here. And then everything in the middle, right? So there's this whole spectrum here. So everything from very slow molecules to very fast molecules. And you're only seeing the curves. So you're seeing, like this curve right here, right? So that's the curve for hydrogen molecules, H2, two hydrogens stuck together, all right? So, but we're imagining that the way they made those curves was they did the same thing we talked about last time. Like, oh, I'm going to watch all these H2 molecules go by. There goes a fast one. There's a really slow one. There's a medium one, a little bit slower, a little faster. And they started stacking these up, right? So this is what they did. They were like, this is the distribution for all the hydrogen molecules that I saw go by and timed with my little stopwatch, right? So, I'll erase all that stuff. So they did the same thing with those hydrogen molecules and then helium atoms, water molecules, nitrogen molecules, and oxygen molecules. All right, so different kinds of molecules here. And they made these Boltzmann distributions for all these different kinds of molecules as they go by. Now, here's what you need to know about this particular distribution. All of these are at the same temperature. Okay, so this H2 sample, we watch these molecules go by, let's say at 100 degrees Celsius, right? These heliums that gave us this curve were also at 100 degrees Celsius. These water molecules, 100 degrees Celsius. Nitrogen at 100 degrees Celsius. O2 at 100 degrees Celsius. So these are all at the same temperature. That's really critical to remember. And we're looking at how many of the molecules are going at a particular speed. So we're seeing at this temperature of whatever it is, 100 degrees Celsius, This is our curve for H2. This is our curve for helium. This is our curve for water. So what I want you to do for Monday is to ponder this, all right? You're going to try to extract as much information out of this graph as you can and try to figure out what it means, all right? Because we've been talking about temperature as if it means the same thing as the speed of the molecules. And under certain circumstances, that may hold true. Now we're looking at an example where we've got 5 different kinds of molecules. They're all at the same temperature. So the way we've been defining temperature, we would say, okay, so therefore they're all going the same speed. What I want you to ask yourself and come in ready to talk about on Monday is that true? Are all of these molecules that are currently being, observed at the same temperature, are they going the same speed? And if not, how are we supposed to revise our understanding of what temperature actually is if it's not simply the speed of the molecules? So give that a try. Think about it. You're welcome to look up anything you want to about this. You're also welcome to just go off of what is in your own head, which is actually what I'm more interested in, because this is some pretty cool stuff, if you ask me, and we're going to work on it together, but I want to get your thoughts on it first. So enjoy the rest of your break, and I'll see you guys on Monday.